Okay, so welcome back to another video. Here's a little quick floor equation problem we would like to solve, and that is to find all real numbers x such that 2 to the power x plus 1 is equal to 2 to the power the floor of x plus 2 to the power x minus the floor of x. It's pretty simple there. It's actually really quick. You just utilize the definition of the floor function, the greatest integer function. In other words, you want to put it that way. It's actually, of course, follows with that definition. You're going to see a bunch of compound inequalities, which makes sense because it follows with that definition of the floor function. So utilizing that idea, and then we're going to get a little bit creative with some algebra. Yeah, it's going to be a quick video, so let's actually just jump right in. So by definition, I'll say this again, many times I'll repeat this. So we know that suppose that if we let the floor of x, we're going to let this equals k, such that for k is an integer. Utilizing that definition of the compound inequality, that has to say that, well, for one, let's first say that 2 to the power x plus 1 is equal to, so replace everything for the floor of x for k, so it's 2 to the power k, and add this with 2 to the power x subtract k. This entails that because that we have that the floor of x is equal to k, this actually implies that specifically we have that the compound inequality is written as follows. So that means, let me actually put a little star next to that as an asterisk just to put more implication to it. So that means we have that k is less than equal to x, which is less than k plus 1. Again, as you see, it follows with, with integers. So it has to follow with this implication from here. And so with this, so now plugging all this back in, well, specifically, not really plug this back in, but there's some observations we want to make. For one, if we just take a look at 2 to the power x plus 1, so for now, we're actually going to look at both sides and then make the comparison and justification of what we're going to say. So for one, we see that specifically, if we look at 2 to the x plus 1, if we put that in the middle of our compound inequality, we can make the observation and see that 2 to the k plus 1 is less than or equal to 2 to the power x plus 1, which is strictly less than 2 to the power k plus 2. And so from here, now another observation we can make is that, another thing is that we're actually looking at specifically the right-hand side, so 2 to the power k plus 2 to the x minus k. From that observation, we see that we have that 2 to the power k is less than, or 2 to the power k then plus 1 is less than or equal to 2 to the power k, then add this with 2 to the power x subtract k, then strictly less than 2 to the power k, and then add this with 2. So what I'm going to do here is that, let me actually label these numbers. So the first part is that the equation given is, we're going to call this equation number 1. I'm going to call this the second number 2. And then we're going to call this number 3. So here we actually have everything we combined together from number 1, number 2, and number 3. For one, we can actually form ourselves a little observation with these inequalities and say that specifically, if we're going to isolate everything from just one variable, so temporarily we're just going to ignore x for the moment and then focus everything on k, just so eventually if we figure out what k is, we can actually make things a little bit easier in terms of finding like what our solution x is going to be. From after forming everything from 1, 2, and 3, we actually get the following systems of inequalities. So we're going to have that 2 to the power k plus 1 is strictly less than 2 to the power k, and then add this with 2. So if we think of it this way, we're kind of isolating everything from the center and taking more approach of like the outer bounds. So we're saying the left is strictly less than the right from over here, and we just apply that same logical thinking from here. 2 to the power k plus 1 is strictly less than 2 to the power k plus 2 for the exponent. So here we have systems of inequality, so we have this equation here, and we have 2 to the power k, add this with 1 is less than 2 to the power k plus 2. And so from here, now what we're going to do now is solving this systems of inequalities, which is not that difficult. We're going to take things one at a time. So what we're going to do here, let's start off with this equation first. So we'll call this, let me just label this as number 4 and 5. Because I wrote this in green, let me just put it this way. So 4 over here and then 5 over here. Let's actually take into approach, look at equation number 4 first. So equation number 4, what we can do from here is we can actually factor out a 2 from both sides. So I have 2 to the power k multiplied by 2 is less than 2, then multiplied with 2 to the k minus 1, and then plus 1. Then of course I can just divide the 2 to both sides. So now I have 2 to the power k is less than 2 to the power k subtract 1, and then add this with 1. And so now what I can do here is let's subtract 2 to the k minus 1 both sides. And so this means minus 1 is less than, I accidentally wrote, almost about to write an equal sign. less than 1. So what I'll do is, for now, let's actually factor out 2 to the power k. So 2 to the power k multiplied by 1 and then subtract. So 2 to the negative 1. So in other words, that's the same thing. I'll write this as minus 1/2 less than 1. Then what I can do is take the natural log of both sides. So I have that ln of 2 to the k. And then in other words, 1 minus 1/2 is, ln of 1/2, which is the same thing as ln of 2 to the negative 1. So I'll change that subtraction to say minus ln of 2 is less than, so ln of 1 is just 0. Then what I can do is, applying the logarithmic properties. I could have done that earlier step, but that's okay. So this will be k, then ln of 2, and then add the ln of 2 to both sides. So this is less than positive ln of 2. And so this implies that we have that inequality that k is strictly less than positive 1. So that actually solves 1 out. So let me actually box this so we actually have one of our solutions figured out. So with that, let's actually move on to equation number 5. So with equation number 5, so we have 2 to the power k plus 1 and then less than 2 to the k plus 2. Let's actually subtract 2 to the k to both sides. So I'm gonna just switch the, I'm just gonna switch the numbers, so that means I'll just flip the sign, it's okay. Plus 2, then subtract 2 to the k, and so that means this is going to be greater than 1. Okay, and so of course I'll just factor out 2 to the k. So this is 2 to the k multiplied by 2 squared, which is 4, then minus 1, strictly greater than 1. So applying natural logs to both sides, so that means I have ln of 2 to the k, and then so this will be plus ln of 3, and then this will be greater than 0. ln of 1 is 0. So we've actually solved all this out using logarithmic properties and all that. So we have k ln of 2 is greater than minus ln of 3, then that has to be that we have that k is now greater than negative ln of 3, and then divided by ln of 2. Okay, and so with systems of inequalities, we have interval solutions. In other words, we actually take the intersection. If you learn this in set theory, we take the ones that's in common in between, and then we actually form ourselves a nice little interval and say that k specifically in between the natural log of 3, ln of 2, and then that's less than 1. So in other words, this has to imply if we're saying k is an integer over here, negative ln of 3 over ln of 2 is basically negative 1.5 something. I can't remember the number, but what that matters is that we know that k has, the integer for k is going to have to be k is equal to 0 and negative 1. So now that we found out what k is equal to 0 and negative 1, all we have to do now is just plug this back into our original, well, rather for the ones that for k, and now we can de-isolate it to say that we can find whatever our x value is. So trying this out, so we have k is equal to 1, or the floor of x is equal to, well, I meant to say negative 1, but let's actually first start it with 0. So if we have that for the floor of x is equal to 0, so that actually plugs that back in to say that now this is 2 to the x plus 1, then this is equal to 2 to the 0, which is just 1, and then add this with 2 to the x. Okay, and now I'm just going to skip the steps here. This is basically just following the same algebra just like we did before, but if actually solving all this out, you're going to get that x is equal to 0. So some solution exists. And on the last part, we have that if we have to find for k is equal to negative 1, the floor is negative 1. So the floor is negative 1. Then that means that if you actually plug all this back in, so we have that 2 to the x plus 1 equals 2 to the negative 1, then add this with 2 to the x plus 1. But what's interesting is that if you were to cancel some stuff out, you're just going to left with no variable is, left to be discovered. So in other words, there is no solution for k is equal to negative 1. And so therefore, the only solution that satisfies this equation is x is going to equal 0. So the only solution exists is just this following right here. And just like that, we actually completed this short, well, I might have just went a little forward with explanation, but it's actually not a lot to do for solving the floor equation with the inequalities, well, from that definition of the floor function. So there we have it. Therefore, the solution for 2 to the x plus 1 equals 2 to the floor of x plus 2 to the x minus the floor of x. The only solution is x is equal to 0, which is indeed a real number. So there you have it. So yeah, that's pretty cool if you ask me.